So good morning one and all. This is the 54th lecture in the series of control system. What we are going to see today is a very important part in control system, and this is kind of a concluding part. So whatever new concepts are there, these are the last new concept that I'm going to discuss today in state space or state variable analysis. Two more lectures will be conducted, and in those two lectures we will be seeing some 4 or 5 different state variable analysis model, and that will be it. So to give you a very brief recap, we started state variable analysis before 5 to 6 lectures. Initially I told you what is state. So if you're taking an RLC system, in that case circuit current, that is the inductive current or resistive current, capacitive current, and capacitive voltage. So for second order system we have to define two state variables. We can define more, but that will be over determined system. We don't want a over determined system. So to explain all the dynamics of a second order system, we have to define maximum two state variables. So we had defined for second order RLC system, that is state variables were inductive current and capacitive voltage. And we had seen what are the different state variable model for RLC system. Now one thing also we have to define, that is what is the output variable. If we take output variable as inductive current, C matrix will be different. If we take output variable as capacitive voltage, then C matrix will be different. So C matrix is called as output matrix, A matrix is system matrix, B matrix is called as input matrix. A matrix is always going to be a square matrix. If there are 3 state variables, dimension of A matrix will be 3 by 3. These things are very easy provided you do all the notes that is uploaded. So nothing is unturned till lecture 53. Whatever things were covered, all the things were uploaded. And do it, because in future if anybody is going for any kind of study in control system or model control theory and all, they will be requiring this state variable analysis. So it will start from here. Whatever basic fundamentals we are gathering, it will start from here. So first we had seen 3-4 different types of numerical, how to develop control system, how to develop state variable model. Then we had been using the state variable model. So once we have found ABCD matrix, so there was a block diagram. That block diagram had explained that B matrix comes first. That was actually the block representation of state variable model. So first there was coming the B matrix, that is the input matrix. Then at the output there was a C matrix, and in between there was coming the state matrix. So there was a feedback kind of a thing, so it is called a state feedback, and there was an integrator in between. I have shown you that diagram. So B matrix comes first, then A matrix, then comes C matrix, and finally the D matrix comes at the top. So D matrix is a very unique thing which is called as direct transmission matrix. So it is connecting between the input and the output directly. So that was the positions of ABCD matrix we had seen. After that we had seen from ABCD matrix how can you find the transfer function. So ABCD matrix is given, C into Si minus A inverse into B plus D. If we do, we can find the transfer function. So this was the first part. Then we entered the second part. There I was giving you the system differential equation. So d2y dt2 plus 5 dy dt plus 3 dyt is equal to something of dxt dt plus something of xt. So yt is the output, xt is the input. So this kind of system equation or system differential equation, if I give you, you are taking the Laplace in both the sides, then you are finding ys by xs. That was the first step. So how can you convert this differential equation into system transfer function? That was the first step. After you are finding transfer function, then you are finding the companion form of it. So this is something which is, it is not difficult, but 3-4 numericals we have done for second order system, third order system. So from transfer function, how can you find state variable model? So there was coming an intermediate step, which was called as a companion form. So I had shown you that 2-3 numericals we have solved. So there was xt, there was yt, and always we were taking that yt is equal to q1t. So q1t is nothing but the state variable, the first state variable. Generally the state variable model is given as q dot t is equal to aqt plus but. Okay, so qt is the state variable model, a state variable vector. Q dot t is the differential of a state variable vector. So q dot t is equal to aqt plus but. So b is the input matrix and ut is the input forcing function. So this was the format of state variable, and yt is equal to cqt plus dut. So this a b c d, all this four matrix, if we can determine, we can say that we have found the state variable model of the system. So some more numericals we will be seeing in coming 2 hours of lecture, and that will be the end of the state variable model analysis. So I gave you the differential equation. From there you found transfer function. From there you could find what is called as the state variable model, and you could find ABCD matrix, provided output is given. If output is not given, automatically you have to take yt is equal to q1t. So once you had found a state variable model from companion form, last thing was, again from this ABCD matrix, try to find out the transfer function. And once you find transfer function, you do the cross multiplication, you take inverse Laplace transform, you can find the system equation. So this is a chain. So this is a numerical we had done. Given was a differential equation, from their transfer function, from their companion form. From the companion form, you are finding ABCD matrix. From ABCD matrix, again you could verify C into Si minus A inverse into B plus D. You could again verify whether it is generating the same transfer function or not. And if it is generating the same transfer function, means it is talking about the same differential equation. So this was another type of numerical. Then we had gone for solution of state variable analysis. So this is the main part which is generally ignored, which is generally not taken, or students also lose interest. But this is the heart of it. If you don't know how to do the solution of state variable analysis, or how to find the actual equation of state variables, then there is no point doing or learning state variable system modeling. Because whenever we have variable system modeling, it might be a 4x4 system. So there may be 4 state variables, and you can write the equation, you can write the dynamics, you can write ABCD matrix. But if you don't know how to find the equation of x1t, x2t, x3t, and x4t in time domain, then there is no point. And you have learned solution of ordinary differential equation in first year and second year. So just application of that we are doing in case of a state variable model. So there are two parts. One is the homogeneous solution. So whenever we are just saying q dot t is equal to aqt, we are not giving any forcing function. In that case, we can find that we have to find something like e raised to at. E raised to at is the state transition matrix, which is nothing but Si minus A inverse, uska inverse Laplace transform. So we find phi t is equal to e raised to at is equal to ILT of Si minus A inverse. And from there we find e raised to at. And e raised to at is the matrix which is actually changing the steps. Okay, so if we just keep on changing the value of t, then you will be finding different states of state transition matrix. If we multiply initial conditions, so if there are two state variables x1 0, x2 0, and that will be given in a column form. So whenever we multiply e raised to at into x0, that gives us the homogeneous solution. What is meant by homogeneous solution? Homogeneous solution is solution of the system where no external forcing function is given, only by the input only by the initial condition. So if I say IL and VC, there might be some initial current, there might be some capacitive voltage already stored in the system before you applied any kind of input. So they actually are responsible for producing the transient response of the system, or zero input response of the system. So in control system you might have done, in signals and systems you might have done that. I have given you an equation like d2y dt2 plus 5 dy dt plus 3yt is equal to 3xt, 3 dxt dt plus 7xt. Then I ask you, xt is the unit step. Find what is the zero input response, what is the zero step state response, and what is the overall response. So one numerical from the book of BP Lathi, I will upload it today. You have done that numerical. So the same thing we are doing here also, okay, but not by direct method of solution, but by state variable method of solution. So whenever there is a system, there are two responses. One response, or the first part of the response, is the transient response, which is caused by the internally stored energy before you had applied any kind of forcing function. So that is given by e raised to at into x0. Second part is the non-homogeneous system response. That is if the system is q dot t is equal to aqt plus but. Okay, that means input matrix is there, ut input forcing function is there. In that case, how could you find out what is the x1t and x2t? So solution of differential equation is the main important part, and which you have to understand. And 2-3 numericals I have done in the class, I have shown, I have uploaded. So please check the steps. Don't get scared. Okay, so this is not about exam and all, this is about learning the actual trick. And these things are not generally asked in the exam because it is not taught properly, students don't understand it properly, but there is nothing difficult. If you understand how to find e raised to 80, just multiply e raised to 80 with x0 and you get what is the homogeneous solution. And second part is you have to do integration 0 to t e raised to 80 minus tau b u tau d tau. So ekdo numerical, if you see, you understand how to do it. Okay, so it is nothing difficult. Only thing is, yes, in exam you might find the answer might not come correct, one thing here and there. If you misplace, that is okay, but you can learn the trick. Always you should learn the trick, and all these things are doable by using MATLAB. So how the MATLAB is solving it internally, that part you are supposed to learn. So that solutions we have done last day. So zero input response is e raised to 80 into x0. That is by internal initial conditions. Zero state response ZSR. That is whatever external forcing function we are giving with respect by that. So that forcing function might change. Sometime it might be ut, sometime it might be ramp, sometime it might be parabolic or sinusoidal. So same system, e raised to 80 x0 in internal part, initial part will be same, but depending on the input given, the ZSR will change and overall system response will change. And overall system response, or x1t and x2t, that will be the addition of zero input response and zero state response. So that solutions we have done last day. So those are the parts. So the second part is very important, that is finding what is the e raised to 80. So finding the state transition matrix, that is the important part. So for two-dimensional, for three-dimensional, I have shown you how to find a state transition matrix. It is only about doing partial fraction and inverse Laplace transform. So 2-3 numericals are solved in every classes, and that is the highest level of difficulty, so don't worry about that. And after that, we had used the state transition matrix to find out the solution of the overall state variable system. So we stopped there, and today what we are going to do is what is meant by state controllability and state observability. So with this lecture actually, so some small numericals are there. It's very easy, all matrix operation, but what is controllability and what is observability, that you have to understand. And there are some numericals we will discuss today. So fundamental wise, this is the last lecture. Okay, but two more lectures will be conducted tomorrow and day after tomorrow, where we will discuss 4 to 5 state variable analysis or state variable model development for circuits and for systems. Okay, so they were important for exams and all those things. So whether exam will happen or not, I'm not going to discuss all those things, but we should be prepared with the full syllabus. So whole syllabus is covered more properly. Only for this last few topics I should not leave it, so I thought of covering it, and thanks to you all for coming here. So first is the question asked in this is a 10-mark question is asked. Define what is meant by state controllability or complete state controllability. So state controllability means complete state controllability, and observability means complete state observability. So I told you what is state variable. So if I say RLC circuit, in that case circuit current is a state vector, in that case capacitive voltage is a state vector, and at every instant of time, how much is the current and how much is the voltage, that is the state of the state variable. So whether I can control the states of inductive current, or whether I can control the states of capacitive voltage. If you're driving a car, what are the states? In that case, the states are speed, direction, velocity, all these things can be states. Okay, so whether by input or by brake or accelerator, I can control the speed every time. Whether by brake, accelerator and steering, I can control the direction and acceleration of the vehicle or not. That is actually called as controllability. So by external inputs, if I am able to control the states, whether I can do it or not. Okay, so that study is done in controllability. Suppose one student is there, I teach him, then also he gets 90. I do not teach him the subject, then also he gets 90. So my teaching has nothing to do with his getting marks. Okay, so in that case, that fellow is uncontrollable. Okay, one student, I teach him, then also he fails. I don't teach him, then also he fails. Okay, so in that case, my teaching has nothing to do with his performance. So his performance and my teaching, they are uncorrelated. So if you take his performance as a state vector, in that case, that state vector is not controllable by my teaching. So it is like that. So I found one student. I was teaching directly in the class, and he was looking outside the window, and he was in his own dreamland. Okay, that means whatever I'm teaching, it hardly makes any difference to him. So he is into his own domain. Okay, so in that case, I can say that system that is between him and me. Okay, it is an uncontrollable system. That is, my words, my voice, my saying is not doing anything to him. So here also a lot of times happen that I teach, and a lot of students, they kept the mobile connected, and they are not there. Okay, so in that case, whatever I teach good or whatever I teach bad, it doesn't matter. Okay, because they are not affected. So definition of controllability, I think as you can find here, so I think my slide is visible to you. Okay, so it is a notes I have prepared. So it's a 8-9 pages notes, and all the numericals and everything is there. Numericals are very easy. Only you have to first form what is the controllability matrix and observability matrix, and you have to find its determinant. If determinant is non-zero, means system is controllable. If determinant is non-zero, then system is observable. So what is a numerical? Numerical is only finding what is controllability matrix. So for A matrix, if it is 3 by 3, controllability matrix also will be 3 by 3. If A matrix is 3 by 3, observability matrix also will be 3 by 3. So finding controllability and observability matrix and checking their determinant. If determinant is non-zero, means system is controllable. For MC, controllability matrix. For MO, M stands for matrix, O stands for observability. So if MO, determinant of that, is non-zero, okay, so singular means zero, non-singular means non-zero. So if the matrix determinant is non-zero, that means it is observable. So our main consideration would be controllability and observability matrix should have non-zero determinant. Then the system is completely controllable and completely observable. So I will repeat that. I have to prepare controllability matrix and observability matrix. So 2D controllability matrix, 3D controllability matrix, that is the most highest level of difficulty. Both we will see here in this numerical. So I have to prepare a MO and I have to prepare a MC, controllability and observability matrix. I have to find that determinant, and I have to see that whether their determinant is non-zero. If they are non-zero, that means they are controllable. If MO determinant is non-zero, that means this is observable. So this is how the numerical is to be done. Now, two things I will teach you. What is the definition of controllability and observability? First thing. And second is how to find the controllability matrix and observability matrix. So let us see state controllability. What is the definition? A system is completely controllable. Completely controllable means completely state controllable. Okay, if every state variable can be controlled in finite time by some unconstrained control signal. Control signal means external input forcing function. So if we are giving some external forcing function, and if we can control every instant of output of the state variable, so every instant response of that state variable, if we can control by the external input, so it is always a non-homogeneous system. Whenever we are talking about controllability and observability, they're always a non-homogeneous system. Okay, that means input is there, external input is there. So a system is completely controllable. So this is the first line of definition that you have to write in a 10-mark question. So question is asked, define controllability, define observability, explain their significance. ये 4 mark. Then 3 marks, one numerical is given, that is find whether the given system is completely state controllable. So you have to find MC, controllability matrix, you have to find its determinant, that's all, 3 marks. You have to find observability matrix, you have to find its determinant, from there you have to conclude. That is also for 3 marks. So these are 10-mark question standard which is asked. The system is completely state controllable if every state variable can be controlled in finite time by some unconstrained control signal. Unconstrained control signal means whatever input we are given, okay, that suddenly should not change. Okay, that should be given, and that is an independent source. Okay, unconstrained control signal means whatever source we are connecting to the system, that system should not be a constrained source. So that system, that input should be a independent source, and no problem with that. So it will be independently inputting energy to the system. So getting those energy, if I am able to control, or if I am able to find out, or if I am able to maneuver every instant of every state variable. So if there are two state variables, many instances are there, t is equal to 1, t is equal to 2, t is equal to 3. So I can maneuver at every instant how much is going to be the state variable by that external input. Then I can say that that system or those state variables are completely controllable. So for a completely state controllable system, it is possible to transfer the system from initial state, that is at t is equal to 0, so x1 0 x2 0, to a desired state in finite time. Means what? Initial state means t is equal to 0. I want that after 5 seconds the inductive current should be this much. I want after 5 seconds the capacitive voltage should be this much. So I have to connect input in such a way that I can define that after certain time this much is going to be the values of state variables. If I can do that, then I can say that that system is completely state variable, completely controllable. So if any state variable is irrespective of its input, so if input cannot control the state variables, in that case we can say that the system is uncontrollable. So uncontrollable system, that means I'm teaching something, so input is given but system is not going in the desired direction, states are not going in the desired direction. In that case it is called as an uncontrollable system. So if controllability matrix has a full rank, now what is a controllability matrix? Be careful, this is the controllability matrix. So how many states are there? There are n states. Okay, suppose if I say n is equal to 3, in that case m stands for matrix, C stands for controllability. So in that case the controllability matrix, if n is equal to 3, then it will be b a b a square b, because you can see for n states, n state variables, it is going to be a raised to n minus 1 into b. So a raised to n minus 1, if n is equal to 3, that means it is going to be a square. So this calls the augmented matrix. So if it is a order 3 system, that means A matrix is 3 cross 3 matrix. In that case B matrix is always going to be 3 cross 1 or 2 cross 1. Okay, for single input we are talking about. So in that case, if B matrix is having 2 cross 1 or 3 cross 1, if A matrix is 2 cross 2 or 3 cross 2, in that case this MC is going to change. Okay, but generally we ask highest for third order matrix, so in that case MC will be B AB A square B. If it's a second order system asked, in that case MC will be B and AB. Okay, so you find the determinant of this augmented matrix. So full rank means if determinant is non-zero, that means it will be having full rank. Okay, if a rank is less, in that case determinant will be 0. Okay, so we will find that. So if controllability matrix has full rank, in that case we can say that the system is completely state controllable. So matrix rank n is linearly independent column of vectors. So in this case a numerical is given, x dot is equal to ax plus bu, A matrix is given, B matrix is given. This is A matrix is 3 cross 3, that means there are 3 state variables. In that case MC will be B AB A square B. So from here first A is given, find A square. Okay, and then multiply B with that. So A square also will be having 3 cross 3, multiply B with that. In that case you will be finding 3 cross 1. So this matrix 1 minus 6 31, this is nothing but A square B. So first you have to find A square and then multiply B with that. Please don't make mistakes in matrix multiplication. You can do it by calci also. What is AB? So just multiply these two. So this is 3 cross 3 and this is 3 cross 1. If you multiply A and B, you are going to get this is 3 cross 1. Okay, and first matrix is B matrix. So for 3-dimensional A matrix, MC is going to be B AB A square B. For 2-dimensional matrix, for 2-dimensional A matrix, MC will be B and AB. So in that case this MC will be a 2 cross 2 matrix. So after you find what is the controllability matrix MC, find what is going to be its rank. So if you are finding its rank, you are finding first 2 terms as 0, third term is 1, so this is minus 6 0, so this is minus 1. So minus hai ke plus hai, it doesn't matter, but the determinant of the controllability matrix should not be 0. Okay, it should be non-zero. If it is non-zero, that means the system is completely state controllable. So as soon as you are finding that determinant is non-zero, any value, positive, negative, anything will do. Okay, controllability matrix determinant is non-zero, it means that the system is completely state controllable. What is the meaning of that? That means if you are giving some external input, with that you can maneuver the system, you can take the system from initial condition to any other values by giving some kind of external input. So this is actually the concept of state controllability. What is the concept of state observability? you have to observe. So you are finding Y matrix. Y matrix is the output matrix. From there, if you can find out what are the initial conditions of state variable. Okay, so actually you are observing the state variables. That means xt, x1t and x2t you are observing. How the state variable 1 is changing. That is inductive current is changing. Initially it was high, then it is falling like this. How the capacitive voltage is changing. Initially it is 0, then it is rising like this. So you can check the whole states of all the state variables in inductive current, capacitive voltage. For RLC circuit, obviously I'm talking about. The whole thing you can check. Okay, so all the measurements. So you are checking output at every instant. You are checking the output at every instant, x1 t and x2t at every instant. From there, if you can find out what was its initial condition, that means what was the x1 0 and x2 0. So from output responses, if you can travel back or find out or figure out what was the initial condition, x1 0 and x2 0. In that case, we are calling that system to be completely state observable. So a control system is said to be observable. So here I have given the definition. Control system is said to be completely state observable or only observable if every initial state x0. So if there are two state variables x1 and x2, that means x1 0 and x2 0 both. Okay, if every initial state can be determined from the observation yk, that means you are finding the output. Actually, you are observing all the states at every instant. From there, if you can calculate what was the initial value might be 0. Okay, but from the at any instant, just from the value of IC or IL or VC, you can find out how much was IL0 and VC0. In that case, we can say that the system is completely state observable. So finally, I'll tell you the definition. Control system is said to be observable if every initial state x0 can be determined from the observation yk over a finite number of sampling period. I mean, you won't have to go to infinity to observe the system. Maybe you have observed the system for 5 seconds or 5 minutes. Okay, so many state variables, many instances of states, many transitions of states have happened. So from all those values, by mathematically, if you can come back and you can tell me, yes, a state variable value was 5 ampere at t is equal to 0, or capacitive voltage initial value was 0.3 millivolt at t is equal to 0. So if this is if you can figure out from every state variable amplitudes at every instant, then we can say that the system is completely state observable. The system is therefore completely observable if every state transition eventually affects every element of the output vector. That means initial value, then e raised to at next state, then e raised to at next state, then e raised to at next state. If it is happening like that, then again you can revert back. So from every step you can find out what was its previous state output amplitude of the state variable. So in state feedback system, we require all state variables should be fed back. So that thing is shown. So if you remember the block diagram of state variable analysis, all the state vectors were being fed and given to the A matrix and it was coming back. So in particularly, however, all state variables are not accessible through the direct measurement. So it happens that if you see the car, okay, we are just giving changing the steering, we are just pressing the accelerator and we are seeing that the vehicle is running faster or it is producing exhaust. What all things are happening internally, it is not measurable. So the very big point why the systems are not completely state observable, it is because all the intermediate variables, all the intermediate transitions, we cannot observe every time. So that is what they are saying, all state variables are not accessible through the direct measurement. So then it becomes necessary to estimate. So whenever it is not measurable, you estimate what is going to be the population of India in 2030. We cannot tell exactly, but we can do an estimate. So whenever I say estimate, it is going in the statistical domain. Okay, so then it becomes necessary to estimate the unmeasurable variables in order to implement the state variable feedback scheme. So it again is going in the domain of statistics. So I'm not going to explain that. What I'll explain is how to find the observability matrix. So you can find MO. Okay, so MC was B AB A square B. So please don't mistake that. It was B AB A square B up to A raised to n minus 1B. If there are 3 state variables, in that case A raised to n minus 1B. So last thing becomes A square B. So for third order system, controllability matrix was B AB. So that is the second column. B is the first column. AB is the second column. A square B is the third column. That's all. Observability matrix. So if it is a third order system, it will be C, that means 1 row 3 columns. CA, again 1 row 3 column. CA square, again 1 row 3 column. Likewise it will go to C into A raised to n minus 1. So if n is equal to 3, that means it's a 3 variable system. Then it will restrict to, MO will restrict to C, CA and CA square. I have given you an example for 2 second order matrix. So you can find A is 1.1, 0.3, negative 1, 0. C matrix is 1 and minus 0.5. So to find observability matrix, you need two state variable model components. One is A, another is C. Okay, and C is generally like this. C is generally row matrix. B matrix is generally column matrix. Okay, that's why if you see MC, that is a controllability matrix, it is B, AB, A square B in the row form, sorry, in the column form. But if you see this observability matrix, it's in the row form, C, CA, CA square, CA raised to 3, likewise. So in this case, A matrix is this, C matrix is this. So find C, CA. So first job is to find or construct what is MO. Okay, what is MO? C and CA, because this is 2 order. If it was 3 order, then it would have been C, CA, CA square. So numericals are shown later. So what is C? C is 1 and 0.5. So C is 1 and minus 0.5. What is C into A? So just put C here and A here. So if you multiply C into A, you'll be getting like this, 0.6 and minus 0.3. What we have found out is this determinant, if you find, so 0.3 into 1. So this is minus 0.3 into 1 is minus 0.3. And plus of this, so minus 0.3 or plus 0.3, they cancel each other. So MO is equal to 0. So whenever you are finding determinant is equal to 0, that means system is not completely state observable, because it is not full rank. So whenever the determinant is coming to be 0, that means this matrix will not be producing full rank. As it is not producing full rank, not all states of the systems are observable. That means it is not completely state observable. That means just from the output, you will not be able to find out what are the initial states of all the state variables. Maybe if there are 2 state variables, for 1 state variable, you might be able to see what is x1 0, but x2 0, you will not be able to see. Okay, so not all states of the system are observable because it is less rank. If MO was equal to 2 or 5 or something, or any non-zero value, then we could have said that yes, the MO determinant is non-zero. That means it is completely state observable. That means all the state value you could find what was the state value at t is equal to 0. But in this case, it is not like that. So it is not completely state observable. It may be partially state observable. Okay, so in control theory, observability is a measure for how well internal states of a system can be inferred by the knowledge of its external output. That means how well we can find out the internal state variable initial value from the any other values. Okay, infer means reason to deduction or established by deduction. So concept of this observability was introduced by scientist R.E. Kalman. So you just search what is meant by Kalman filter. This is the biggest mathematical filter design which had happened in 1960s. So Rudolf E. Kalman, R.E. Kalman, so he was felicitated by US President Obama somewhere in 2006 or something. So I think he is still living. So just check out. There are huge amount of pages on him in Wikipedia. So what is Kalman and what is Kalman filtering? And there is no field of science or there is no field of engineering where Kalman filter is not applied. So whenever there is a system which is continuously changing, like satellite, okay, like vehicles, okay, how to find the next state? So from the previous state, how to find the next state if the system is a time varying system? Okay, so Kalman filter is used, and there are various methods and there are various different types of Kalman filter which have been originated from the basic Kalman filter which he had invented. So Kalman filter itself is a very big thing of research. Okay, so just check what is Kalman filter, and MATLAB functions are there by which you can do Kalman filtering. So you are now doing DSP and DTSP, all those things. So you can have some applications, all Kalman filtering. So a lot of examples, experiments, and all those things are done. In my PhD, I could apply Kalman filter for state estimation of the system, fuel cell system that I was estimating. So this is called as Kalman observability. Whatever definition we are seeing, this is called as a Kalman observability. That means from any state, we are able to find out what is the value of its initial state. This is called as Kalman observability, and how to find it we will see by numericals. So controllability and observability describe structural features of a dynamic system. So ये ABCD matrix find करके होता क्या है? Okay, this is actually the structural feature of a dynamic system, mathematical feature of a dynamic system. These properties play an important role in model control system design theory. The condition on controllability and observability often governs the control condition. So if we know what is the controllability, if it is completely controllable or partially controllable, then we can design the control theory depending on the controllability and observability of the system. A plant is said to be completely controllable if every state xt0 can be affected or controlled to reach a desired state in finite time by the unconstrained control ut. So move the states from one state to another without disturbing the system. That is actually the feature of controllability. And observability, I told you that any instant you check the state variables. From there, if you can come back to what was its value at x1 0 and x2 0, what was its value at t is equal to 0, if you could find that, then it is completely state observable. Okay, so like looking at me, so I'm 43 years old, just looking at me, you could tell me when I was born, how was I? Okay, so if me as a state variable, okay, my whole body and physics is a state variable, just today looking at me, this is the present state of state variable of me, you could estimate or you could find out what was I at day one. Okay, so that is actually called as observability. But not all the variables in the system are measurable. Okay, so a lot of internal things are there, happens in the system. From outside we cannot measure it. So that's why most of the systems are not completely state observable. Most of the systems are partially state observable. So this much knowledge at this stage is enough. If you can define what is controllability, what is observability, and if you can find it. How to find it? So some numericals are there. So 4 pages I have written, notes I will upload. This whole document will be uploaded today. So I think this thing is visible. I have given you a 2 by 2 matrix. So it's a system x dot t is equal to axt plus but. So A matrix is 2 3 0 5, B matrix is 1 3. Question is find the controllability and observability. So what is controllability matrix? MC B AB A square B A raised to n minus 1B. So now here n is equal to 2 because it's a 2 by 2 matrix. Okay, that means MC, that is a controllability matrix, becomes only B into B and AB. That means first column is B. So B is given. Here it is B is given. So numerical is given at the top. I'm sorry. Okay, so B matrix is given as 1 3. A matrix is given as 2 3 0 5. So whenever I'm defining controllability matrix, always for 2-dimensional matrix, MC will be BAB. It is written for n is equal to 2, or when A matrix is 2 cross 2, MC will be BAB. Whenever it is a matrix is 3 by 3, that means there are 3 state variables. In that case, MC will be BAB A square B. That's all. These are standard rules. So now our A and B, all these things are given. So for the given system, AB is equal to 2305 into 1 3. So first multiply A and B, get AB. It is also going to be a column matrix. So what is controllability matrix? It is B and AB. So B was given as 1 3. Please don't mix up the row and column. Okay, because in all this numericals, keeping row column separate, understanding row column is very much important. So controllability matrix is B and AB for second order system. So B matrix is 1 3. AB just now I have found here. Very simple matrix multiplication. You can do it by calculator also. So now AB is 11 and 15. And then find what is the determinant of controllability matrix MC. So it is BAB. So this is 15 minus 33. So this is 15 minus 33. So in case of RH criterion, we do the multiplication. This 3 and 11 we do first, minus 1 and 15. This is what we do. But in case of matrix, we start from top left and we go to the bottom right. That is 1 and 15 minus bottom left and top right. So it is 15 minus 33. That is minus 18. Minus 18 hai ke minus 100 hai ke plus 18 hai, doesn't matter. It is non-zero. That is the important thing. So what are the steps? For second order system, MC is going to be BAB. B is given. AB I have to find out by multiplication. Had it been a third order system, I had to find out A square B. So one another step of multiplication I have to do. So in the second order system, I have found first what is controllability matrix. Then I find what is the determinant of controllability matrix. I find it to be non-zero. Whenever it is non-zero, the conclusion I have to write. So generally, most of the time students do what? They find determinant of controllability matrix not equal to 0. Udhar hi chhod dete hain. And we don't give them full marks. This one line is very important. That is, the given system is completely state controllable system because the determinant of controllability matrix MC is non-zero. As determinant is non-zero, that means it is not singular. That means it's a full rank controllability matrix. As it is a full rank controllability matrix, that means all the states are completely controllable by the external input. So ये एक line, sorry, ये एक statement 3-4 line का तुम्हें last में लिखना है. So this is the procedure. For the same system, if output matrix is given, so now previously input matrix was given 1, 3 or something. Now A matrix is same, output matrix is given as 3 and -1. Question is find whether the system is state observable or not. So what do we do? First thing we have to find out, so n is the number of state variables. As A matrix is 2 cross 2, that means there are 2 state variables. That means we have to find C, CA, CA square, CA raised to n minus 1. So CA raised to 2 minus 1 I have to go up to. So if you substitute n is equal to 2, so you are finding C and CA. Okay, so for n is equal to 2, that means second order system, that means the system with 2 state variables, the observability matrix will be C and CA. Okay, for 3 state variables, this is not the numerical, we will see 3 state variable numerical next. Okay, for 3 state variable system, that means where A matrix is 3 cross 3, the observability matrix will be C, CA, CA square. And please don't make mistake in these dimensions. B, AB, A square B is written in a row format. C, CA, CA square is written in a column format. And what is C matrix? 1 cross 3. What is CA? 1 cross 3. What is CA square? 1 cross 3. So this MO, okay, will be also a 3 cross 3 matrix. So always remember that the dimension of A matrix will be same as dimension of controllability matrix and dimension of observability matrix. I will repeat, dimension of A matrix will be same as direction of controllability matrix and dimension of observability matrix. You can check here, previous numerical, it was a 2 by 2 matrix, A matrix was 2 by 2. Okay, so that's why we found controllability matrix was also 2 by 2, and we will be finding that observability matrix is also 2 by 2. So A matrix is this, C matrix is 3 minus 1. So for second order system, observability matrix MO, that is equal to C and CA. Okay, C and CA. So what is C? C is 3 minus 1, and CA you have to find separately. So C and A. Whenever I'm saying C and A, don't do A and C. Okay, C and A means C will come first and A will come next. So C matrix is 2 cross 1, sorry, 1 cross 2, and A matrix is 2 cross 2. So if you multiply 2 cross 1 and 2 cross 2, so sorry, 1 cross 2 and 2 cross 2, you will be finding this matrix is going to be 1 cross 2. That means 1 row, 2 column. Okay, because C matrix is having 1 row, 2 column, 1 cross 2. A matrix is having 2 cross 2. So if you multiply this, it will be 1 cross 2. So this is 6, 4. So this 6, 4 comes below. Okay, so top one is 3 minus 1, that is C matrix. Bottom one is CA, that is 6, 4. Now you do the cross multiplication. So this is 12 plus 6, that is 18. So 18 hai ke 20 hai ke minus 18 hai, doesn't matter. Only thing is the observability matrix is 3 minus 1, 6, 4, and its determinant is non-zero. Determinant is non-zero means it is having a full rank. Full rank means all the states are completely observable by the system. So as the determinant of the observability matrix is non-zero, given system is completely state observable. So writing this statement at the end is very important. Without writing this statement, full marks will not be given to you. So you can do anything because it's a very easy numerical, kuch hai nahi isme. So if you are not able to give a judgment, then marks will be deducted. So the main thing is find MC, find MO, find determinant of MC, find determinant of MO. If the determinant is non-zero, that means system is completely state observable, completely state controllable. Same numericals, this is nothing different. We are doing for higher dimension system. Okay, so x dot t I have taken is equal to axt plus but, and yt is equal to cxt plus dut. Okay, that means so D matrix का कोई role नहीं है इसमें, only A, B and C matrix. So if you're talking about controllability matrix, it's only determined by B and AB and A square B. That means A and B. So only the first equation is sufficient if controllability is asked. Okay, and A matrix and C matrix both are required if observability is asked. So I have asked both. Okay, so A matrix is 3 cross 3 matrix, B matrix is 3 cross 1 matrix, C matrix is 1 cross 3 matrix. What is the matrix? What is the value? That might differ. So in exam, definitely the same question will not be asked. Okay, so you have to check. First, find you have to that is a controllability matrix. So what you have to say is, as is a 3 cross 3 system, controllability matrix MC will be B A B A square B. So B matrix, you know, 102, and observability matrix will be C C A C A square. So please write it properly and don't look at any book. Different books are having different notations. So some book they write MC as B A B A square B either transpose, and MO is equal to C C A C A square. Likewise, some book write MC is equal to B A B A square B in uh, a row form, but they write MO as C C A C A square also in a row form, and there is a transpose here. Okay, so ज़्यादा इधर उधर देखो मत. Whatever I am giving, it is correct, and understand the concepts this way. Only you have to calculate what is the determinant of controllability matrix and observability matrix. So first I have found A square because A square is required in MO as well as MC. Then I find, after finding A square, I'm trying to find what is B, AB, and A square B. So first I have to find controllability matrix. So first column is B. So B is 102 given, and then AB. Okay, so I have found AB. So AB is somewhere below. So A is 201, 032, minus 1, minus 2, 0, and B is this. So if you multiply, you are getting 4, 4, minus 1. So AB I have written as the second column. And A square is 3 minus 2, 2, and all those things. So I have not checked it actually. I have done the calculation and I found the result and got it. So you can do the same calculation, or by MATLAB you can verify and you can let me know if there is any mistake. But only thing is you have to check for B, AB, A square B. So first I have found B is given, A is given. So first find A square. So multiply A square with B. So you are getting 7, 10, and minus 12. So this 7, 10, minus 12 is put here. So first column is B, second column is AB, third column is A square B. So for A square B, first you have to find A square and then multiply B with that. Okay, and A square B is not same as B A square. Okay, so matrix you have to put matrix properly. So A into B is equal to B into A. For matrix it is not like that. Okay, you have to put it properly. So A square B means A square should come first and then come B, and A square already is found first. A square B, AB. So AB is the second column, A square B is the third column. And after finding controllability matrix, then what you do is find what is the determinant of controllability matrix. So controllability matrix determinant is found like this, and this you can calculate by your calci. So that facility you have. So after finding, you are finding that determinant is minus 14, which is non-zero. So that means as the determinant of the controllability matrix is non-zero, the matrix is completely state controllable. So if it is 0, then what? Then you have to find rank. Okay, so how many ranks? So 3 state variables are there. That means it's a 3 by 3 matrix. So maximum rank can be 3, minimum rank can be 0. If it is 0, that means none of the state is controllable. If rank is 1, that means out of 3, 1 state is controllable, 2 are uncontrollable. If rank is 2, that means 2 states are completely controllable, 1 state is not completely controllable. But in this case, we are finding that determinant is non-zero. That means rank is full. That means all 3 states in this case will be completely state controllable. So that is a controllability. Finally, it is observability. Okay, so what is observability? We have to find C, CA, CA square. Likewise. Okay, so 3-dimensional observability matrix given by MO, C, CA, CA square. So C is given and CA is given and CA square. So A square is given. First find what is CA square. So this is C and this is A square. We are finding CA square is minus 5, 7, and 4. What is C? C was given minus 1, 1, 0. And what is CA? So with C, multiply A. So you are finding this. So C is given as minus 1, 1, 0. So this is the observability matrix you have to see. Okay, so observability matrix MO, that is C first. So minus 1, 1, 0. Then there is CA. So C into A, if you're doing minus 2, 3, 1. So minus 2, 3, 1. And CA square. A square I have found in the previous page. So CA square is minus 5, 7, and 4. So this is actually observability matrix. So when we check your answer sheets, first we check whether all the 9 entries in the controllability matrix and observability matrix, they are perfectly done or not. If they are done perfectly, then only we give full marks. Otherwise, no. Okay, generally we find that one or two rows, one or two columns, they are correct. Third row or third column may be mistake. Okay, so first find what is a square. After finding a square, अच्छे से लिखो book में. Then multiply a square into b. Do that multiplication and write in the book. Okay, then write a square c into a square. Write in the book c into a. So ये थोड़ा लिख के करो, because this is a 10 mark numerical and does not even take 10 minutes. Okay, more than 5 minute भी नहीं लगता है. Okay, ये करने में. So go slow and don't make mistake in this numerical. So C C A C A square. This is the very important thing. C C A C A square you have to write like this. C matrix is a 1 cross 3 matrix. CA will be 1 cross 3 matrix. CA square will be 1 cross 3 matrix. So that's why MO also will be a 1 cross 3 matrix. And you find out what is the determinant of that. You're finding the determinant is coming to be -2, which is non-zero. Then finally you have to write the conclusion, that is, as determinant of observability matrix is not equal to 0, the system is completely state observable. That means all the states, just from the all the state at any instant, you can find out what is the initial value of all the states at t is equal to 0. That means from every state you can find out what is x1 0, x2 0 and x3 0. So as per its inventor, this criteria is called as Kalman observability. So this finishes control system. This finishes all the fundamentals of controllability observability. This finishes all the theory of state variable analysis as per your syllabus. All the numericals are solved. Okay, so we will do some more numerical on 3 or 4 numerical we will do on state variable system modeling, and that will be the end of lectures. So all the fundamentals are done. Now 2 more lectures with some more numericals on state variable we will do, and we will call it a that's it. So tomorrow and day after tomorrow, I would like to take some lab sessions, 1 or 2 hour of lab session. So Bode plot numerical I will upload today, tomorrow, that you do. On state variable analysis, we have to do a lab, that will be lab number 9. Okay, so what are the functions, how to find solution, how to find ABCD matrix from the given D2Y, DT2 and ODE equations. That thing I would like to show. So 2 more lectures and 1 session of lab, and that will be the end of all the control system lectures and lab in this semester. So I stop here today. This notes and this lecture will be uploaded by today. Please listen to it. That's all. Thank you.